Good morning once again. So we'll start with the remaining problems what were left in the last class. So from this time I'll be writing the questions so that it will be more clear for all of you. So the next one, a system is composed of 10,000 parts. A system is composed of 10,000 parts. What average failure rate per part must be achieved to get the systems mean time between failure of 250 hours. Assume series connection. Assume all parts are connected in series. Assume series connection. So what is given? A system is composed of 10,000 parts. So that is given is n is equal to 10,000 parts. Okay. Then what average failure rate per part be achieved to get, that means they have asked us to find failure rate per part must be achieved to get the systems. Here also given, what is given? Mean time between failure of the system is given. Mean time between failure, that is theta, S represents system, is given as 250 hours. But we know that failure rate is equals to 1 by mean time between failure. Hence lambda is equal to 1 by 250. It is but it is failure rate of the entire system. It is failure rate of the entire system, but we want the failure rate per part. But how many parts are there in the system? We know it is 10,000. Hence, this answer you divide by 10,000. So the answer is 4 into 10 raised to minus 7 parts. So the next problem. The mean time between failure of a certain unit is 50 hours. The mean time between failure of a system is 50 hours. Calculate the reliability for 75 hours. Calculate the reliability for 75 hours. Calculate the reliability for 75 hours of operating period. Of operating period, full stop, of operating period. Then if the reliability of the unit is, if the reliability of the unit is increased by 10%, 20%, 30%, 40%, and 50%. If the reliability of the unit is increased by 10%, 20%, 30%, 40%, and 50%, calculate the first bit, the corresponding percentage changes in MTBF corresponding percentage changes in mean time between failure and then plot a graph of percentage change in reliability of percentage change in reliability versus percentage change in mean time between failure. Now, what is given? The mean time between failure of the system is given. that is theta is equal to 50 hours, that is of the system is given, and calculate the reliability for 75 hours. To find the reliability of the system for theta is equal to 500 hours and T is equal to 75 hours. And then if the reliability of the unit is increased by 10, 20, 30, 40 and 50%, and we need to calculate the correspondence change, percentage change in mean time between failure. But first we will find out the reliability of a system, that is reliability of the system is equal to e raised to minus lambda t, we know, that is, but lambda is 1 by theta, that is the mean time between failure, it is 1 by 500 hours, which is equal to 2 into 10 raised to minus 3. E raised to minus lambda is 2 into 10 raised to minus 3 and operating time t is equal to 75 hours. The reliability of the system with the given data will come as 0.8607. We'll assume it as 0.861. So here the reliability is 0.861. Now we need to calculate the percentage change in mean time between failure if the reliability is increased by 10%, 20%, 30%, 40% and 50%. So first we will consider when the reliability is increased by 10%. So the value of reliability is 0.861. If it is increased by 10% means we need to multiply by 1.1. Hence the reliability nu is equal to 0.861 into 1.1, which will be 0.9471. This is the new reliability for 10%. So for this 10% we need to calculate what is the percentage change in mean time between failure. So substitute this value in the reliability equation, that is R is equal to e raised to minus lambda t, and reliability nu is 9471 is equal to e raised to minus lambda we need to find, and with the same operating time of 75 hours. So if it will become the ln of this, it will be minus 0.0543 is equal to minus lambda 75. Hence lambda is equal to 7.24 into 10 raised to minus 3. I'll just write this, the new reliability over here. The reliability of the system, what I calculated is 0.861. But I am not interested in failure rate, but I am interested in mean time between failure, which is 1 by lambda, which is So this is for 10%. So this is for 10%. That is for 10%. And similarly, we need to do the same procedure for 20, 30, 40 and 50%. 20, 30, 40 and 50%. So it will come as 138.1, I guess. And similarly, you do it for 20%, 30%, 40%, 50%. And then what you can do is that you can just plot the graph over here. On one side, the reliability, the other side, the mean time between failure, that is the new. So here for 10% increase you write, for 20% increase you write, for 30% increase you write, for 40% increase you write, and for 50% increase you write. Here also for 10% what is the, just I'll take same itself. Here it is coming in 100, so I'll take 100, 200, 300, 400 and 500. And then you just plot the data and the data will come like this linearly. So you can do that. So what does it represent? As the reliability increases, the mean time between failure also increases linearly. The next one, a cassette player has four subsystems, namely, that is, first one is the speed control system, speed control system, and the magnetic pickup head, the magnetic pickup head magnetic pickup head. The third is amplification. Amplification and sound systems. Amplification and sound systems. And the fourth is other systems. And just write it as others. Systems, other systems. So for a satisfactory performance of a cassette player, all four subsystems must perform satisfactorily. The mean time between failure of various systems are, for a satisfactory performance, all subsystems must perform satisfactorily. Satisfactorily. The mean time between failure of various subsystems are, failure of the first part 2000 hours, and for the second part 2500 hours, and for the third part amplification and sound systems it is 4000 hours, and for the fourth part, that is the other systems, the mean time between failure is 3000 hours. Calculate the reliability of a cassette player. Of a cassette player for 1500 hours, for 1500 hours reception time. What is the mean time between failure of a cassette player? So here there is a cassette player which are 4 subsystems, that is the speed control system, the magnetic pickup head, amplification and sound system, and other systems. So also they are given the mean time between failure of all the 4 systems, that is the mean time between failure of the first, that is the speed control system, is 2000 hours. Second, that is the magnetic pickup head, 2500 hours. Mean time between failure of amplification and sound systems is equal to 4000 hours, and mean time between failure of other system is equal to 3000 hours. That is nothing but the given data. And then they have asked us to find out the reliability of the cassette player for 1500 hours, which is nothing but the time period. And also they have asked us to find out the mean time between failure of the cassette player, which is nothing but the theta. So, but they have asked us to find out the mean time between failure of the cassette player, which is a system comprising all the subsystems, hence it is nothing but the theta of the entire system. So first we need to calculate the reliability of a cassette player. So that is nothing but the entire system. So we assume that, but they have mentioned that for a satisfactory performance all subsystems must perform satisfactorily. What does it mean? That means if any one of the subsystem fails, then the cassette player will not perform satisfactorily. For the satisfactory performance of the cassette player, all the 4 subsystems must perform satisfactorily. That means what kind of system it is? It is a series connection, isn't it? Because here in series connection also, if any one of the system fails, then the entire cassette player will not perform satisfactorily. So here it consists of 4 parts, that is, I am just going to write it in short. Acoustic and sound and other systems. So if all these 4 systems perform satisfactorily, then only the performance of the cassette player is satisfactory. If any one of the system fails, then the performance of the cassette player is not satisfactory. Hence, first, in order to find the reliability of the system, we need to find out the failure rate of each of the parts. So for this first one, FCS is equal to 1 by 2000 hours, and which implies over here the failure rate of this is 1000 divided by 1 by 2500, and here it is the failure rate of acoustic and sound system is equal to 1 by 4000, and here also the failure rate is of other systems is equal to 1 by 3000. .33 into 10 raised to minus 4. So the unit here is failures per hour, But for a system connected in series, we know that the failure rate of the entire system is the addition of the failure rates of the subsystems. Addition of the failure rates of the subsystems. Addition of all the failure rates of the subsystems, here it is Hence, the failure rate of the entire system is it is 14.83 into 10 raised to minus 4 failures per hour. Now we can find out the reliability of the entire system, which is e raised to minus lambda t. The t value is again what is given as calculate the reliability forecast 1500. 1500. So it will come as 0.1081. So that we have calculated the reliability, and they have also asked us to calculate the mean time between failure of the entire system. So that is theta s will be 1 by failure rate of the entire system, which is 1 by 14.83 into 10 raised to minus 4. That is 674.3 hours. So this is also calculated. The next, we'll solve 2 more problems and then we'll proceed with redundancy. The next is, what is the failure rate of a piece of equipment? What is the failure rate of a piece of equipment what is the failure rate of a piece of equipment if the probability of survival is 88%, for 900 hours. For 900 hours. Of operating period. Express the failure rate in terms of percentage failures per 1000 hours. Per 1000 hours. Now, what they ask us to find is the failure rate, and they have asked us to then express this failure rate in percentage per 1000 hours. Now, what is given but? What is given in the problem? The probability, the failure rate of a equipment is asked, but the given is the probability of survival is 88%. So that is nothing but the reliability itself. 88% is nothing but 0.88, and operating hours T is also they have mentioned, that is 900 hours. Hence we know that R is equal to e raised to minus lambda T, and R is given as 0.88 e raised to minus lambda we need to find, and T is 900 hours. So the lambda will come as 1.41 into 10 raised to minus 4 failures per hour. But here we want it in percentage per 1000 parts, hence 4.1 into 10 raised to minus 4, percentage means into 100 per 1000 parts. Per 1000 hours. So that means it will become as 1.41 10 raised to minus 4 into 100 into 1000. So it comes as 14.1 failures in percentage per 1000 hours. The last problem, a 750 hours life test, 750 hours life test is performed on 6 components. Is performed on 6 components. First components fail, that is one component fails after 350 hours. Fails after 350 hours of operation. All others survive the test. and remaining parts survive the test. All others survive the test. Compute the failure rate. So given is number of items are 6, among them 1 item fail and 5 survives. But this one item fails after a service period of 350 hours. So other 5 components survive means they will survive for the entire lifetime, that is 750 hours. So we are asked to find out the failure rate. Now the failure rate lambda is equal to, we know that the failure rate lambda is equal to number of items failed divided by total test duration. Total test duration. How many items have failed? That is given as 1. And what is the total test duration? The total test duration here can be calculated as how many total time all the 6 components have survived. But we know that among 6, 1 of them have failed. So 1 of them has failed up to an operation time of 350 hours, and remaining 5 components survive up to an operation time of 750 hours. This is the survival and this is the failure. Hence the lambda is equal to (2.43) into 10 raised to minus 4 failures per hour. Failures per hour. Now I hope all of you know till now that how to calculate the reliability, how to calculate the failure rate, and how to calculate the mean time between failure of any system. And we also know how to calculate the reliability when the components consisting of a systems are connected in series and when the components consisting the system are connected in parallel. And we also know that when the systems are connected in parallel, the reliability is more compared to the systems connected in series. Now I will talk much more about now something called as redundancy. So we have discussed what we mean by redundancy is that is nothing but duplication. That is nothing but duplication, and may require why we need to involve duplicate parts in any assembly or a system. What happens is that we have discussed that if the assembly consists of 10 parts, if a system consists of 10 parts, and among them one part is very critical and the lifetime or the reliability of that component is very less compared to the other parts, but that part is very critical for the satisfactory performance of the product. In that case, what we do is that we add one more component as a duplication for the ninth part. In case during working, if the ninth part fails or if the critical part fails, which is having the less reliability fails, then this one more duplicate part will do that function, because of which the reliability of the entire system is enhanced. So I'll just give an example over here. I'll take a system in series. Okay, and this is the input and this is the output. I consider three systems which are three parts which are connected in a series to form a system, that is part A, part B and part C. I'll assume the reliability of part A is 0.7 and I'll assume the reliability of part C is 0.8 and I'll assume the reliability of part B is 0.5. The reliability of part A is 0.7, part B is 0.5, part C is 0.8. Now, the reliability of the entire system when connected in series, we know that it is the multiplication of reliability of part A, part B and part C. So it will come as 0.28. 0.28. Now, which part is having less reliability? That is this, isn't it? So to enhance the reliability of this system, I'll make one part among this a redundant part. So I'll choose the part which is having less reliability or the part which is less reliable. Here it is part B. So here it is part B. I'll just make part B a duplicate part. Part B a duplicate part. But the reliability of the part will remain same. Now, what is the reliability of this new connection? Instead of B, I'll just make it as B dash because I have used a redundancy factor over here, and but this is nothing but a system connected in parallel, isn't it? So this is nothing but a system connected in parallel. Hence, RB dash is equals to, we know that for a system connected in parallel, the reliability is given as 1 minus the parts connected in series. Here it is B1, I'll assume it as 1 and here it is 2, and 1 minus B. 1 minus B1 and 1 minus B2. Here I have done this as B dash just because to represent this as a redundant part, and hence the value will come here as 1 minus 0.5 into 1 minus 0.5. It will come as 0.75. So this is the new value of reliability when this part is connected in series, parallel. So the old system was like this: A, B, and C. Here was the input and here was the output, and the reliabilities were like 0.7, 0.5 and 0.8. So what I altered is that I have made one more part redundant to this, because this is the part which was having less reliability or which was less reliable. So what I did is I made a duplicate for part 2. So here, if this part fails, this will perform the function of this part, hence the entire system works. So again, the reliability is 0.7, it is 0.5, and it is 0.5, and it is 0.8. But I calculate the reliability of this is RB dash as 0.75. Hence, A is again 0.7. Here, I'll represent this system as B dash, because this is B and this together is represented as B dash, and the reliability of that was calculated and it came around 0.75, and this is again 0.8. Now if you calculate the reliability of this new system after incorporating the redundancy for part B, it will come as the reliability of new system .42. And here it is 0.828. So if we compare this with this, what we can notice? This is considerably higher than this. That means this system is more reliable than this system. This system is more reliable than this system. What does it indicates is that just by removing the part, if the system consists of parts which are connected in series, we need to look for the part which is having less reliable and then make a duplication for that part which is less reliable. That means we need to make a redundancy. By doing that, the efficiency, or you can say the reliability of the entire system is enhanced to a significant level. Here it was 0.28, it was enhanced to 0.42. So that is the importance of redundancy. So now just make a note of a problem with respect to redundancy, and we'll solve this in the next class. A system consists of 3 components. A system consists of 3 components: A, B and C. A, B and C. This is as shown in the figure. Calculate the reliability of system calculate the reliability of a system. Input and reliability of A is given as 0.8, reliability of system B is given as 0.7, and reliability of system C is given as 0.9. So just try this. In the next class we are going to solve this. Thank you.